Hello everyone, and welcome to our first lesson in mechanics, where we'll dive right into kinematics. As I mentioned in the intro video, we'll start each lesson with our particular goals for the session. After this session, we hope we'll be able to define the scope of kinematics, distinguish between displacement and distance travel, and distinguish between velocity and speed. We can't start talking about kinematics without knowing what this subject includes. Giving a definition, we say that kinematics is the branch of classical mechanics that describes the motion of points, objects, or system of objects without reference to the cause of motion. Because we're only considering its motion and its path, an object can be thought of as having any composition and any shape in kinematics. Now that we know the definition, we can further ask ourselves, what can we say about the motion of a body? Well, consider the motion of a body that goes from point A to a point B on a given path, just like depicted in the picture. You might wonder how far the body is from a given point at a given instant. Well, we use position to answer this question, which is defined as the location of a body relative to a given point. In the picture, I depicted the position of P, a point on the path where our body might be at a given time, from a random point on the plane O. It's interesting to note that it is not enough to specify the distance between the body and the given point to specify position. There are infinitely many points but the same distance from O. That is the definition of the circle, in fact. To get a unique point P on our path, we need to specify direction as well. We can do that in more than one way. In the one-dimensional case, we can use the plus and minus signs of the axis to show the direction relative to the positive direction of the axis. We can use cardinal points north, south, east, west, or we can use orthogonal system of coordinates. It all depends on the specific situation in which way of describing direction helps us solve the problem. Whenever we encounter such a physical quantity that needs both magnitude and direction to be well defined, we call it a vector. It is not always position that characterizes the motion of the body. It's often useful to consider the displacement, which is defined as the change in position of an object. Note that the final initial positions that we have to subtract to obtain displacement have to be taken relative to the same point in the plane. Usually, that point will be the origin of the motion A on the picture. Because it is a difference in positions vectors, displacement is also a vector, so we need to specify its magnitude and direction. Distance can also be measured by the distance traveled, defined as the total length of the trajectory between two given points. Because distance traveled involves a given path, there is only one way we can measure it. Once we know its magnitude, we can just draw it on the picture, as I did with the curved red line. Therefore, unlike displacement, distance traveled has magnitude but no need for a direction. We say that such a physical quantity that is well defined by giving only its magnitude but no need for direction is a scalar. We are often not only interested in positions of bodies, so where they are at a given time, but we might also want to know where they are going and how fast they are going. We answer these questions by measuring the velocity of the body. There are two ways in which we can measure velocity. We can find the average velocity of a body, which is defined as the displacement divided by the time of travel. However, we can also find instantaneous velocity, which is the average velocity calculated for a really small time interval, which gives the average velocity but at a specific given instant in time. Because it is defined as a rate of change of displacement, velocity also has to be a vector, so we need to specify its magnitude and direction at all times. A scalar analog of velocity is the speed. However, the analogy is not perfect, as the definition for average speed and instantaneous speed are not quite similar. Average speed is defined as the distance traveled divided by elapsed time, whereas instantaneous speed is just the magnitude of instantaneous velocity. Because here we're talking about distance traveled, and the magnitude of a vector, speed is a scalar. Now that we learned about all these physical quantities in such a short time, a quick quiz can help us check our understanding. Consider the attached picture. We can say that we start from point A and we go on our right to point B on a distance of 10 meters. From point B, we can go to point C, which is 10 meters far. From point C, we continue our journey to point D, which is again 10 meters, but on this time to the left. Note that the points A, B, C, and D form a perfect rectangle with lengths 10 meters and 2 meters. A natural question we might ask is how far from the initial position, which we say it was A, have we traveled until we reach the final position, which was D? Well, I'll give you a couple of minutes to think about this question, and then I'll walk you through my train of thought. Well, this was a trick question, in fact, because there is more than one right answer. Remember that we learned two ways in which we can measure how far we traveled. Your first thought might have been that we can consider displacement and think about the change in position as we went from A to D. Well, consider that we start at point A, our position there will be 0. We are in the point that we consider the fixed reference. Then we end in point D. So there's displacement from A to D just be the line that unites those points. And because ABCD is a rectangle, that line will have a length of 2 meters. However, don't forget that when we talk about displacement, we have to mention direction as well. And for that, I attached a compass there. And know that D is southern than A. So if we consider displacement in answering the question, we'll conclude that we traveled 2 meters towards south. However, that's not our only option. We can consider the distance that we traveled and calculate how long we walked around the path. Well, from A to B, we walked on 10 meters. From B to C, we walked an additional 2 meters. So in total, we had 12 meters so far. From C to D, we add another 10 meters that we walked, so we have 12 plus 10, 22 meters walked. That is the distance traveled. Therefore, both formulations at 2 meters towards south or 22 meters answer our question, although in kind of very different ways. Note that it's always better to specify what we want from a problem. If we want displacement, that is the only thing we need to calculate. If they ask for distance traveled, we have to look at that scalar. However, such vague question can be answered in more than one way. So maybe we should have to make sure that we consider all the options. Well, as this lesson ends, I hope that the main takeaways would be that to describe motion, kinematics studies the trajectory of points, objects, or system of objects that from the physical quantities that we define and consider, position, displacement, and velocity are measured by their magnitude and their direction, so they are vectors, and that distance traveled and speed are the scalars that we consider, measured only by their magnitude. Thank you for your attention, and I'm looking forward to our next session, and when we'll continue to talk about kinematics and introduce even some additional physical